This is Chapter 5, Forces. When we look at a person riding a bike, when you ride a bike, your foot does what against the pedal? Pushes. And when you drop something, it is linked to the ground by gravity. Pulled. So when we look at what forces are a push or a pull or an action that has the ability to change motion. Forces can increase or decrease the speed of a moving object, and forces can also change the direction in which an object is moving. We rely on forces basically for everything that happens. So when we make a list of these, they can make objects start moving, stop moving, move faster, or move slower. And this would be our speed. And they can make objects change directions, and they can make objects change shape. Think about a balloon. You apply a force to a balloon and you can change the shape of a balloon. Forces can cause a change in speed or direction. So in the last chapter we just talked about it. When you have speed with a direction, it is velocity. So we can say that forces cause a change in velocity. And we talk about a change in velocity, we call that acceleration. So forces cause acceleration. So it ties our two chapters together. Forces are created multiple ways. It could be by you with your muscles, wind, or even gravity. There are 4 elemental forces that we are going to talk about. All forces in the universe come from only 4 basic forces. Example is electromagnetic forces, which are important to technology, and gravity, which is universal force because it's pretty much everywhere. There's no place where there's no gravity. There's places where there's microgravity. So our first one is strong nuclear force. This reviews back when we talked about atoms and how they're held together. 2 is electromagnetic force. And again, this takes us back to how you have molecules and how they're held together. And then you have the weak force, which is this is basically related to radioactivity, and gravity, which we all know what gravity does. It holds everything together from the attraction. And your weight is what is caused of gravity. Forces are usually measured in newtons, abbreviated with a capital N. And forces usually act, you think about if there's a push, there's a pull, so they act in pairs. And forces will act in a particular direction. And forces usually cannot be seen, but their effects can be seen. Something falls, you see the object fall, but you actually cannot see the gravity that caused it to fall. The pound is a unit of force commonly used in the United States. So when you measure weight in pounds on a postal scale, you are measuring the force of gravity acting on an object. So when you step on your scales at home, you are actually measuring the pull of gravity on you. So if you're measuring gravity, which is a force, technically it shouldn't measure pounds, it should be measuring newtons. So though we use pounds in our everyday life, scientists do stick with using the newtons. And a newton is a smaller unit of force than the pound. If 1 pound of force equals 4.448 newtons, then 100-pound person weighs 444.8 newtons. So this is the scientific description of weight. When you look at force, as we said before in our last chapter, we use vectors that we draw to represent force. So again, you look at the XY axis kind of thing. You can show strength of the force and direction of a force by using an arrow. One way forces act is the result of direct contact. So a contact force, now at the bottom of your note taker you have a little box, so you'll be defining this and then writing examples of these in. Contact force is basically exactly what it says. It's transmitted by matter directly touching other matter. So it's the direct contact that, for example, like a wind acting to slow a parachute. Then your action at a distance, or I call it also non-contact, because there's no direct correlate touching of the two objects. They are affected by the force, but not directly touched by the force provider. Okay, so example is gravity. Again, you cannot see it, but it will show the effect of the results. So here you have the categories of contact forces: is friction, normal force, tension, air resistance, and spring. At a distance forces is gravity, electricity, which we've already talked about, and magnetism. So going over the specifics, springs. Springs are used to make or control forces. The force from a spring always acts to return the spring to its resting shape. So this information here, the force created by a spring is proportional to the ratio of the extended or compressed length divided by the original resting length, basically is stating this in a nutshell. If you stretch a spring twice as much, it makes a force that is twice as strong. So basically, think about a rubber band as similar to a spring. As you pull it back a little bit, it's not going to snap back as much as if you pulled it back twice as much. So we have different springs that will do different functions, whether they're compressed springs or expanded springs. Gravity. The force of gravity on an object is called weight, which we talked about. So we talked about this too when we talked about potential and kinetic energy. Potential energy, remember, was mgh, and our gravity we always identified as 9.8 newtons. So that is what it is on Earth. So weight and mass, though, are not the same thing. Mass is a fundamental property of matter, measured in kilograms. Weight is the force, measured in newtons. But weight depends on mass and gravity. So the more mass that you have, the more gravity has to pull, so therefore it increases the weight. But when you look on the moon, so we're comparing the gravity from Earth to moon, a 10 kilogram rock on Earth is only 98 newtons. And on the moon, the 10 kilogram rock will be 16 newtons. So if you want to lose weight, you can go to the moon, but you realize that your mass will not change, so you're still going to look the same. You'll still have the same amount of mass. Friction is another type of force, and this is the force that resists the motion of objects or surfaces. There's many kinds of friction that exist, and we're going to hit on some of those throughout some of these examples. So friction depends on both the surfaces in contact. Here is an example of fluid friction. So when a hockey puck slides on ice, the thin layer of water between the rubber and the ice allows the puck to slide easily. Now when we talk about fluid, this can be a gas or a liquid. A lot of the times you see lubricants used to reduce sliding friction, because fluid friction is a way to get rid of the direct contact. Hovercrafts use the same thing. They push a flow of air out the bottom to put a cushion between them. Air hockey is the same thing. you think about lubricants, any sort of fluid friction you have, oils and greases that are used in ball bearings and maybe like skateboards and rollerblade wheels, or even in your car, you need oil for the pistons to be able to move like they need to get your engine to continue to run. Another type of friction is static friction. This is a frictional force that's measured in newtons, just like all the other forces, but this is the friction that keeps an object at rest. It keeps it from moving. Every single object experiences static friction. Static friction, you have your book sitting on the table, it has static friction, keeps it from moving. Sitting in a chair, you have static friction, it keeps you from sliding out. Static friction is with everything, but you have to think about the larger the object, the more static friction it will have, which means it requires more force to overcome that static friction. Sliding friction. You overcome that static friction, you begin to slide the object. Now it's sliding friction. This is a force that resists the motion of an object moving across the surface. So again, it depends on what the surface is. The rougher it is, the more sliding friction you're going to have. So even more mass is going to cause greater slider friction, so it's more force. Writing on your paper with a pencil is sliding friction. Falling on the carpet and getting rug burn is sliding friction. Unless a force is constantly applied, friction will slow all motion to a stop eventually. It is impossible to completely get rid of friction, but it can be reduced. Ways to reduce friction is by, one, using wheels, by placing like maybe ball bearings in a piece of machinery to reduce it. Putting wheels on a chair reduces the friction of sliding it across the floor. It's easier to use a dolly to move a refrigerator because it has wheels than to try to slide it across the floor. You can also reduce friction by using gases or fluids like we talked about with fluid friction when we talk about oils and maybe greases and things like that. Using friction. Friction is also important to anyone driving a car. Now this could be you soon because you're all at that age where you are driving, or you're going to be driving, or getting a car. Is important to understand the tires. Grooved tire treads allow spaces for water to be channeled away from the road tire contact point, allowing for more friction in wet conditions. This is helpful this time of year for us. So it is important that your grooves are in the tires, and if they get worn down, you're going to have that water come between your tire and the road, and then you can hydroplane. Not good. So these are the tires that we use on our everyday cars. Tires that race car drivers use are flat on the bottom and do not have any treads, because the more contact they have with the surface, the more friction they have, and this allows them to have more forward force to go faster. But the bad part is, if it rains on a race day, they have to completely stop and dry the track because it could be very dangerous. If you notice also, people who drag race their cars, they will do burnouts beforehand to heat up the tires to make it even more friction with the stickiness of the heat from the tires turning on the pavement. And even race car drivers in the Indy 500 and the Daytona and stuff, when they do their warm-up lap, they drive in a zigzag back and forth, warming up their tires before they actually start the race. So friction can be beneficial, but it could also be dangerous. Again, here, you know, friction creates heat. You can get rug burns from it. You can rub your hands together, get heat, but eventually it could cause a fire. Forces in equilibrium. The sum of all the forces of an object is called net force. We talked about this when we talked about vectors. So we take in consideration all directions of the forces. So we have an upward force of 55,000 newtons and a downward force of 50. And a 20,000 newton to the left and 20,000 newton to the right. And we know these cancel each other out, so there's going to be no motion to the right and left. But because of the difference between the up and down, we end up with a net force of 5,000 newtons upward. When we look at how planes actually function and fly, there's a lot of forces to take in consideration. You have weight, the drag, which is the air friction around the body of the airplane, and the thrust of the engines to put it forward, and the lift force caused by the flow of air over the wings. When you look at an airplane wing, it looks as it's called an airfoil. The whole purpose is the design is to get the fast air to go over top of the wing. Fast air creates air particles to move farther apart, which creates a low pressure. Which creates low pressure. So if you have low pressure above and fast air above, that means you have slow air below the wing, which is not moving, so it's condensed. It's very dense, very close together, which means it has a high pressure, which means it has an upward force creating lift, which lifts the plane up into the sky. Now, the similar process can happen if you have a person who wore a skirt on a windy day and it was raining, so they had an umbrella. And if the wind comes around the umbrella, not under the umbrella, and that's what everybody seems to think, that's why umbrellas turn inside out, but it's really due to the fast air moving on the outside of the umbrella, because then underneath the umbrella is the slow air, which has a high pressure, which then pushes up inside the umbrella, flipping it inside out. And the same thing with the skirt or a dress. So you have the fast air moving around it, and underneath you have the slow air, and then you create a lift force underneath, flipping your dress up. Equilibrium. We kind of talked about this. Net force is 0, and when we have a net force that is balanced and it's 0, we say the object is in equilibrium. So normal force is not on your paper. You need to add this to the bottom of your note taker. So the normal force is the upward force, and the book automatically naturally has a downward force, but they are the same, so we say that they are in equilibrium, and we know that because the objects are not moving. So here you have, again, the normal force showing that's an equal strength to the force pressing the object into the surface. As I said, the downward force. Every time you walk, the floor pushes up on you as you push down on it, and it's usually at the same strength, unless you have an added force causing more motion. So that is chapter 5 on all the forces. We will experience the forces through the stations. So come prepared with your note taker done.